Hi everyone, welcome back. In previous lectures, we had discussed what rollups and coprocessors are, how they work, and when to use one versus the other. Today, we are going a level deeper. We'll look at the different types of coprocessors that exist today, how they differ in design and trust models, where they shine, and what trade-offs they bring to the table. So without further ado, let's dive in. Before we explore all the types of coprocessors, let's establish the core challenge we are solving. Traditional security focuses on protecting data at rest, like files on your hard drive, and data in transit, like information traveling over the internet. But what about the data in use, when it's actively being processed? For off-chain computing, this becomes critical. We need to process complex computations outside the blockchain, all the while maintaining security guarantees that comes with the blockchain. The question is, how do you trust computation happening somewhere else? This is where the coprocessor approach comes in, each offering a different solution to the trust problem. First up, we have TEEs, or Trusted Execution Environment-based coprocessors, which enable hardware-based confidential computing. A trusted execution environment creates a protected system where data is isolated from the other processes at a hardware level. This approach to confidential computing protects data while it's being processed using specialized hardware enclaves. Now, why would you even want to use TEs in the first place? Well, the advantages of using TEs are pretty compelling. Firstly, in terms of performance, they offer near-native speed for complex computations. In terms of efficiency, there is minimal computational overhead. Moreover, in terms of managing cost, they are one of the most economical flavors of confidential computing for large-scale deployments. But as always, there's a trade-off. Placing trust in the hardware vendor. Intel, AMD, or ARM essentially become a part of your trust model. Let's take a real-world example with Marlin's Oyster. Marlin is a verifiable computing protocol that leverages TEs to deploy complex workloads over a decentralized cloud. Instead of running expensive computations on-chain, Oyster processes them in TEs or secure enclaves and returns verified results to the blockchain. This enables us developers to build applications that are impossible to build using just on-chain resources. We had discussed one such example in the previous section as well, where we wanted to run a machine learning model while maintaining cryptographic guarantees. Next up, let's examine zero-knowledge coprocessors, or as some like to call it, the trustless alternative. ZK coprocessors offload complex computations from the blockchain using zero-knowledge proofs to ensure correctness. Here's the key insight. Instead of trusting hardware, you trust mathematics. Why choose ZK coprocessors, you ask? They offer a completely trustless security model. The ZK proof itself guarantees the computation was performed correctly, without revealing the underlying data or requiring trust in any central authority. However, this mathematical elegance comes with a cost as well. The performance takes a hit due to the ZK proof generation being very compute intensive. In terms of efficiency, there is significant overhead compared to native execution. Since ZK heavily relies on complex math, it is difficult to implement and expensive to scale. ZK coprocessors excel when trustlessness is paramount. Think regulatory compliance, cross-chain bridges, or any scenario where participants can't or won't trust a central authority. Now, the maximalist approach. Fully homomorphic encryption coprocessors. Unlike ZK coprocessors, which focus on scaling computations off-chain, FHE specializes in maintaining absolute data confidentiality during computation. The data never gets decrypted, not even during processing. FHE rollups typically rely on fraud proofs for verification, creating an interesting hybrid approach. The benefits are unmatched. In terms of data privacy, your sensitive information never exists in plain text during computation, ever. We can consider it as pure cryptographic trust since there is no reliance on hardware or any third party. But, as always, there are trade-offs. The performance is often hundreds to even 1,000 times slower than native computation, and the costs are severe, as this approach is extremely resource intensive. FHE coprocessors are reserved for scenarios where privacy trumps all other concerns. Think medical research, financial analysis, or government applications with strict confidentiality requirements. Finally, multi-party computation, or MPC, represents the distributed approach to coprocessing. MPC coprocessors split computations across multiple parties, ensuring no single entity ever sees the complete data. It's like having a group calculate their average salary without anyone revealing their individual pay. There are some clear advantages to computing through this approach. We can assure trustless behavior through decentralization, as there is no single point of failure or trust. It's also collaborative in nature, so it's perfect for scenarios involving multiple distrusting parties. But such coordination has its costs. Honest majority assumptions require most participants to behave correctly. There is a high overhead because both computational and network costs increase. Relatively, there are higher chances of communication bottlenecks due to the constant secure messaging between parties, slowing everything down. MPC shines in consortium scenarios, like multiple banks jointly analyzing fraud patterns or competing companies collaborating on industry research. And that's it. Thank you for attending today's lecture on types of coprocessors. In our next lecture, we'll dive deeper into the working of TEEs, the different type of TEEs that exist today, and the pros and cons of using one over the other. See you then.